Okay, there we go. That should be working just fine now. Yeah, it still behaves kind of weirdly when I switch between scenes. I thought it would be okay because I thought the issue was is when I have the same audio track on two different scenes. Then when I switch between the scenes, it seems to muck up, but clearly that's not the case because those were two totally separate audio tracks and it still went a little bit weird. But oh well. Anyway, hello everybody that's here. So, as you can possibly tell from the description, today I'm going to talk a little bit about the sun and stellar structure more generally. So we kind of started the wrong way around. Last week we started by talking about Mercury, when of course really we should have started with the center of the solar system, which is the sun, but I guess the order doesn't matter too much. So yeah, that's what I'm going to talk about today. Now I'm prefacing all of this by saying I'm not an astrophysicist. So this is everything I know about astrophysics, pretty much, is what you can reasonably figure out on the back of an envelope. I don't have a good memory for these kind of things. So if anyone asks me anything about spectral classes of stars, you probably won't get an answer. I will defer to one of my mods. One of my moderators is an excellent astrophysicist. So if there's a question in there, he knows who he is when I'm talking about him. He can feel free to chip in because he's much more experienced than I am in this. Okay, so along that vein, we're going to be talking about stars, and we're going to be talking about stars from the perspective of what we can calculate and what we can work out about them, rather than what we can sort of state and memorize about them. So here is a little view of our sun. This is sped up. How many times is this sped up? This is sped up like 3,000 or maybe 30,000 times. So it looks like a big orange ball. It looks pretty tame and pretty nice in this picture here. But really what a star is a constant kind of stalemate between the explosive nuclear fire that is trying to blast the star apart and the force of gravity that is working to crush the star down. And for most of a star's life, these things are in total balance. And we'll model this with an equation very shortly. But the really interesting things that happen to stars is when one of these forces gets the upper hand. This is like when things start to go supernova or when stars collapse into compact objects. But we're not really going to talk about that today. We're going to focus on the more, I guess, what you might call slightly boring part of the star's life, which is the main sequence. This is the part of the star's life they spend the vast majority of their time in. So it is important to understand. Because, of course, if you're thinking about how long a star will live for, the time that it's in the main sequence, if you can try and calculate how long it will spend in the main sequence phase, this is pretty much how long it will live in total. Because generally it's a very small, it's a fairly small fraction of the total lifetime that stars spend outside of the main sequence phase. So let's zoom in a little on the sun, and let's slow it down a bit so we can properly look at things. If we zoom in very closely, you can see these sort of beehive-looking things. And the way these are shown here, these are convection cells. So just like you might see if you have a cup of tea or a cup of coffee or something, particularly if you use something like oat milk or almond milk, because these have slightly more little particles in them, which aid you seeing this, you can see these little convection cells forming. And this center region here, I don't know, can you see my cursor? You can see my cursor, okay. These center regions here are where material is convecting upwards, the hotter parts, and then as it gets towards the surface, of course on the surface of the star, it's much more easy for things to radiate away energy to cool down. So things will heat up, they'll come up towards the middle of this convection cell, then as they cool, they will sink back down along these edges here, which forms this sort of beehive looking pattern. And there's another interesting structure on the surface, which are these sunspots. Now, I think that the temperature of our sun is something like around 6 or 7,000 Kelvin. I may have got that wrong. But these sunspots anyway are like around 1,000 to 1,500 Kelvin cooler than the rest of the sun. And I think the mechanism that makes these things so much cooler is quite interesting. It's also quite complicated, so I far from understand it fully. But roughly it's to do with the magnetic field of the sun. So the magnetic field towards the outside of the sun is pretty turbulent, because the sun is this kind of big turbulent, rotating and sort of slightly swashing ball of plasma. The magnetic field is not as uniform as the Earth's. So the Earth's magnetic field is relatively well behaved. It pretty much just comes out of the poles and goes back in at the other magnetic pole. Whereas the sun's kind of bubbles and boils over the side a little bit. And these sunspots are regions where the magnetic field is kind of spilling out of the sun. And the presence of this magnetic field affects the paths that the particles take on the surface that would otherwise be taking part in convection, convection is a mechanism of moving heat out of the sun. But because the convection is interrupted, let me pause it here, by the presence of this magnetic field spilling out, this causes these regions here to be quite a bit cooler than the rest of the sun, because they're not able to have as much heat delivered to the surface. So these are 1,500 Kelvin cooler than the rest of the sun. And I think it was observed that these have cycles of around about 20 years or something. And by studying these sunspot cycles, people in the early days of solar physics were able to learn quite a lot about the sun as a whole. And I think they're still objects of significant interest. How these coronal jets and coronal mass ejections work is all to do with the magnetic field of the sun. And this is highly relevant if you're thinking about things like solar flares, which can originate from the sun, because these things could, in theory, be pretty destructive on Earth. Enormous pulses of plasma and electromagnetic radiation could be very damaging to the Earth if it was shot towards us. So understanding these patterns in the sun's magnetic field is very important. Okay. So we want to try and think about these things a little more quantitatively. We're going to try and think about the dynamics of what's going on inside the sun. So the gist of what we're going to do is we're going to think about the different forces that are in balance inside of the sun. We're going to derive some equations that describe the structure of the sun, or of stars more generally, but we're going to apply it to our sun. And then, hello Alan MD. And what was I saying? And yeah, then we're going to try and derive these so-called scaling relations that tell us how things like mass, luminosity, temperature, and radius of stars are related to each other. Then we'll use this to get a relation that tells us roughly how long stars stay in the main sequence phase. So it will explain how the mass of a star affects its lifetime. And then we'll talk sort of a little qualitatively about energy generation in the sun. Stevenson. What does that mean? Stevenson 2 to 18 is greater than sun. I don't know what that means, sorry. But yeah, anyway, then we'll talk a little qualitatively about energy generation inside of the sun, and we'll explain how this actually happens, because a calculation we'll do... Oh, are these names of other stars? Yeah, if you're talking about stars that are bigger than the sun, there are certainly a lot of those. Our sun is relatively average. I mean, it's not perfectly average. I think our sun is bigger than something like 85% of most other stars, but that still makes it relatively average. A little bigger than average, I think. Well, other than other main sequence stars, I mean, I think. Oh, these stars are better than the sun. Well, I mean, what do you mean by better? Because I don't think any of those support life. Our sun is pretty well equipped, that it has a nice sort of extended habitable zone that has our planet in it, and life is pretty great, so I think the sun is nothing to complain about. But yeah, so we'll explain how it is that the sun actually generates energy, because a calculation we'll do will make it appear that the sun shouldn't be able to take part in fusion at all. But there are two mechanisms that help the sun undergo nuclear fusion in the core. And we'll talk about those qualitatively and sort of indicate how you could calculate these things quantitatively if you wanted to, but it's a sort of quantum mechanical calculation. So I thought I'd try and keep things relatively classical for today, just to not turn anybody off if we start doing a tunneling calculation. Okay, so the topic today is stellar physics. Our sun will kill us at some point, yes, but I think probably we'll all be dead and humanity will all be gone quite a bit before that anyhow. No, it doesn't become a neutron star or a white dwarf. Well, actually, will it become a white dwarf? Isn't it just sort of slightly... It's either just on or just slightly below the limit that it'll become a white dwarf. I think our sun, it'll form a planetary nebula anyway, where the outer layers will just kind of be blown off by radiation pressure, but I think it will leave behind a white dwarf. Again, as I say, for those of you that missed the disclaimer at the start, I'm not an astrophysicist. Everything I roughly know about astrophysics is stuff you can figure out on the back of an envelope, so I will forget this stuff. It is massive enough for a white dwarf. Oh, okay, right, I thought so, that's good. Okay. Yeah, quantum mechanics is fine. I agree, but we'll maybe save that for another time. I've just realised the chat window is placed slightly inefficiently. There we go. That's better. Okay. So, stellar physics. Well, let's first note down some useful things about our sun. And these are things you could... that are measurable, not calculated things. That would be quite an envelope. Yeah, well, I mean, it's a big envelope, I guess. Oh, I should also say, speaking of the envelope, the particular envelope I've written these things down on in advance, you can again find on my website if you like. If you go in the About section, you click on my website, then if you go to where it says Twitch office hours, right at the bottom, there'll be a PDF that says something like stellar structure calculations or stellar physics calculations, something like that. So if you want to follow along by reading or point out if I've made a mistake on the notes or there's an inconsistency on what I've written to what I'm saying, then feel free. You can download those there. Okay, so let's talk briefly or state briefly some useful things about our sun that we'll use pretty throughout. Okay. And like I said, these are all things we can measure. So the radius of our sun is about 6.96 times 10 to the 8 meters. And the mass of the sun, which I'll probably call ms. Sometimes they use the symbol, so if you can see this a lot of the time if you look these things up. A solar radius often is an R with a little circle and a dot in it. The little circle with a dot means that it refers to the sun, and likewise m with a little dot would be the mass of the sun, but I'm just going to use S, I think, because it's too much effort to draw the little circle and the dot. With the thickness of my pen it looks a bit weird. Okay, and the mass of the sun will take to be around 1.9 times 10 to the 30 kilograms. Okay, so I mentioned forces that are present in the sun. We said that the sun is just this perpetual battle between gravity that is trying to squash it down and forces due to the immense heat generated by nuclear reactions that are trying to blow it apart. Okay, so let's look a little more detail at these forces. Forces present in the sun. So to start off with, the inward pressure is the most simple to deal with because it only has one source. and that is due to gravity. So gravity is the only source of inward pressure that is compressing the Sun inwards. So if you think about the Sun, that's not the Sun is very nearly spherical. What we're going to do throughout most of this is we're going to consider a kind of layer of material, a sort of spherical shell of material of some particular radius. Okay? No, chat doesn't have to be quiet, not at all. Please yourselves, chat amongst yourselves, whatever you like. Nope, you're not talking too much. No problem at all. What we're going to talk about, what we're going to think about a lot is we're going to think about a spherical shell of material quite a bit. This is what we'll do to derive most of these equations. And the reason we do this is because the Sun is, to a very, very good approximation, spherically symmetric. So we're sort of turning this like we did when we were talking about Mercury last time. We turned it into a one-dimensional problem using this spherical symmetry. And we're doing the same thing with the Sun. Okay? So there's material inside of this particular radius. This ring of material, or rather this spherical shell of material that I've drawn at a radius r here. Yeah, just like a spherical cow. But a slightly better approximation than that. So within this ring, within this shell of radius r, there's a lot of material in here. And this material here, of course, has some mass. And it's going to gravitationally attract all of the material outside of this sort of inner radius here. Sometimes this is called Newton's shell theorem or something. It's like the mass version of Gauss's theorem. It just says if you've got, a spherically symmetric mass like this, then if you're sat at some radius here, the gravitational force you feel is just the same as the total mass that is enclosed within the sphere that you're sitting on, and it feels like a point mass at the center of that. Okay, so this ring here will only feel a gravitational effect from the mass that is inside of this radius. So we will call the mass that is inside the radius r m as a function of r. So mr tells us how much mass is enclosed interior to the shell of radius r. Okay, so that's all the mass inside of this radius r is given by mr. So of course m of the radius of the Sun is just the mass of the Sun, as an example. Yeah, it's Gauss's law, exactly, except it's the sort of the mass version. I think the mass version actually came first because, Newton was working out all of this stuff long before we knew about electric and magnetic fields. So he had it before Gauss's law, but Gauss's law is the complete equivalent for electric fields. That's right. Okay. And what about outward pressures? Well, there are a few different sources of outward pressure. The one that we'll be thinking about, which is the most important for main sequence stars, and main sequence stars the size of our Sun, is thermal pressure. So by this I mean the same thermal pressure you get, inside of a balloon. If you have a balloon full of air, this pressure is generated by collisions between the molecules inside of the balloon pushing out on the wall. It's the same kind of pressure that is present inside of the Sun, that will dominate inside of our Sun. Secondly, there's radiation pressure. This is a pressure due to photons that are produced inside of the Sun in these nuclear reactions, coming out and being absorbed by these outer layers. So within this ring here, there are photons produced by reactions interior to this shell, and some of these photons are absorbed by this layer here. And photons, of course, carry momentum. They have no mass, but there is a formula that links the momentum of a photon to its energy. So they have a momentum given by their energy over the speed of light, and they can transfer some of that momentum to this shell, and transferring momentum is just like transferring pressure pressure is just momentum flux. It's how much momentum is absorbed by the shell per second per unit area. That's an equivalent way to think about pressure, is as momentum flux. And thirdly, there is degeneracy pressure. And this is really not present at all inside of the Sun or inside of any stars other than compact dead stars. So things like white dwarfs and neutron stars. In white dwarfs, this is an electron degeneracy pressure, where that comes, again, it's a quantum mechanical effect that comes from the fact that electrons can't be squashed all into the same space. Electrons that have the same quantum numbers, the same quantum state, can't be put into the same spatial position or into even approximate spatial positions. That's why white dwarf stars are prevented from collapse, even though they no longer produce this kind of nuclear heat that is producing a thermal pressure to keep them up. Instead, it's a degeneracy pressure. Exactly, Pauli's exclusion principle. And neutron stars, it's the same thing, but it's neutrons. Neutrons are fermions. They're a composite fermion made from 3 quarks, but still a fermion. Okay. So for our purposes, this is what will dominate inside of the Sun and during the main sequence phase. Radiation pressure does become more important for very large suns. I think if the Sun is bigger than about 100 solar masses, then it becomes a lot more important. So if you have these super red giants and things, these are mostly supported by radiation pressure rather than thermal pressure. But because we're mostly talking about the Sun, we won't worry too much about that. Okay? So let's try and model this. I said earlier that for most of a star's life, these two forces, this inward pressure that is produced by gravity, is balanced by this outwards pressure, whatever the source of the outwards pressure is. Be it thermal pressure for suns like the main sequence, like main sequence stars like our own Sun, or be it radiation pressure for these supergiants, or degeneracy pressure for compact stellar remnants. Yellow giants are super rare, only 10 known. Oh, really? Yeah, I don't think I've ever actually looked at it. A yellow giant, that's interesting. Okay. And we call this balance between the inward pressure and the outward pressure hydrostatic equilibrium. Where neither one of gravity or the outward pressure force has the upper hand. These things are totally balanced. Okay. So this just means inward pressure equals outward pressure. Okay. So let's model these things. Again, we're going to draw this diagram of a star, and we're going to consider a layer within the star at some radius r. Shrink it down a little bit. Okay. So this inner part of the shell here will be at a distance r away from the center. And we're going to say that the thickness of this shell is some small thickness dr. Okay, like a differential. So what is going on? Well, the shell here has some mass. And the mass of this shell is gravitationally attracted to the mass of all of the material that is on the inside of the shell, that is within a distance smaller than r of the shell. So remember, we had a name for the mass of the material that is inside of this ring. We called this m as a function of r. This is what our function meant. It's the mass within a radius r. Then the mass of the ring itself, well, the approximate volume of the ring, if this is a very, very thin thickness dr here, you can kind of imagine taking this shell and sort of flattening it out. And if you flatten it out, if this thickness is very, very tiny, then this inner radius here is more or less the same size of this outer radius here. So they have approximately the same surface area. Well, it's almost 4 pi dr. It's 4 pi r squared dr. Yeah, exactly. There you go. You caught yourself. Yeah, quite right. So that's the approximate volume of this piece here, this whole spherical shell with thickness dr. And we're going to say that it has density rho as a function of r. Because in general, the density of the star will change depending how far out you are. The further in you are, the greater the pressure is forcing things together. So we can expect the star to have a larger density towards the core. Now later on, we will do all sorts of terrible approximations where we're trying to derive approximate back of the envelope calculations. And we will do stuff like saying we assume the density is constant. And this is a bit naughty, but for the purposes of very quick and sort of dirty calculations, it's fine. We won't worry too much about it. Okay. But let's model the gravitational pressure that results from this gravitational attraction. The gravitation between all of the material that is within the radius r and the mass of this shell itself. Okay. So the force of gravity between these two things is Newton's constant, just using Newtonian gravity here, is the mass of the inner part of the star times by the mass of the shell. And the mass of the shell we've figured out here is this 4 pi r squared rho r dr. So let's comment quickly on what we mean, or why it is we're using Newtonian gravity, not general relativity. So Newtonian gravity is fine for this kind of thing. It's pretty much fine for working in all but the very, very largest stars. But if we were trying to do this analysis for something like a neutron star or even a white dwarf star, then rather than using Newtonian gravity, we would have to worry about general relativity a little bit. And maybe we can do that another time. But today, of course, because we're only talking about stars like the Sun, we're just going to use normal Newtonian gravity. Okay? And then this is, of course, all over r squared. This is just applying gmm over r squared between the layer and the inner part of the Sun. Okay. And pressure is the force divided by the area over which it's exerted. So the force pulling the shell inwards over the area over which the force is exerted on the shell. And this area is just the area of the shell itself. So this 1 over 4 pi r squared will cancel this 4 pi r squared, and we'll just end up with this equation. Okay, that's our pressure equation. The pressure due to gravity felt at a radius r. And now in hydrostatic equilibrium, as we said before, this balances the net outward pressure due to these nuclear reactions occurring. So this is the inward pressure. Now let's calculate the outward pressure. So throughout, we're going to be thinking about thermal pressure. Let me just copy this diagram. Because as I said, radiation pressure is only really having a big effect if you've got stars that are sort of 100 solar masses or larger, and degeneracy pressure is only important inside of very compact stars. So on the inner ring of this shell of material, we have some outward pressure that I will call P at R. And people sometimes get confused about pressure, but the pressure of a gas acts equally in all directions. Okay? The thing that causes a force is not pressure, it's a difference in pressure. So we have to think about the pressure that's on the other side of the shell. And this pressure will be different. Now we're no longer thinking about the pressure at the radius r, we're thinking about the pressure on the other side of the shell, which is r plus dr. And we can kind of imagine in our heads, we can predict that this pressure here will be less than the pressure PR. And that's because simply the pressure further in has to support a greater weight on top of it, because there's more material further in. You know, when you increase the radius out, there's more material. So the pressure that is further out will be larger, will be smaller rather, than the pressure that is further in, okay? So PR will be bigger than PR plus dr, which it makes sense because we expect this pressure to have a net outward push to it, because it has to balance gravity. So we can balance these things. We can say that this outward pressure, we assume PR is bigger than PR plus dr, because of the argument I just said. And this pressure is balancing the gravitational pressure, which we just calculated. Oh, also, we missed something here. In copying down from this line, copying down from this line to this line, we missed out the dr, which is actually very important. So this should have a dr on it. Apologies for that. Okay. So the outward pressure due to, in this case, thermal pressure, but the way we've written it here, this could be due to thermal or radiative pressure, we haven't specified, is balancing the inward gravitational pressure. And if we kind of rearrange things a little bit, I can rewrite this left-hand side in the following way. I've taken sort of a net minus sign. Yeah, exactly. dp by dr. Very good. So I take a minus sign through both of them, and then I divide by dr. So now I have to pick up this minus sign here, and I have still an mr, a rho r, and an r squared here, 1 over r squared. And this thing here, as you make dr very, very small, which is what we would like to do because a lot of what we've done relies on it being quite small, and we want to zoom in on a particular radius. We don't want to think about a really thick wedge of star. So we want to take dr going to 0 as a very, very thin slice. And then this quantity here is just simply the derivative. Well, let me write it on the next page, actually. So that implies this thing becomes the derivative of p with respect to r, as you pointed out in the chat, exactly. So we have the derivative of the outward pressure with respect to r, and then this is equal to this left-hand side here, minus gmr rho r over r squared. So this is our first equation of stellar structure. This is often called the hydrostatic equilibrium equation. It's purely just an equation balancing the pressure forces outwards with the pressure forces inwards, okay? So this describes the balance between outward pressure and inward gravitational pull when a star is in hydrostatic equilibrium, so in the main sequence phase, for example, okay? So let's derive another equation. This equation is even more straightforward. It'll only take a minute or so to derive. And this is called the mass continuity equation. It's just an equation telling us that the mass of the star is conserved, basically. It's telling us how to find the total mass of the star from the density. So if I want to find the mass of the star up to some particular radius, mass is just density times volume, but of course we don't have a uniform density, so we can't just times the volume by 4/3 pi r cubed. Instead, we have to integrate the volume. So this little thin slice of shell, remember, was 4 pi r squared dr. So it is the volume of this small shell of star times the density. So we integrate this up to the particular radius. And these R bars here are just to show that this is an integration variable. It's a dummy variable. It doesn't matter what it's called. It's just good practice not to call it R, because R is the limit you're integrating up to. Okay. And we can invert this equation, as is usually how it is written, just by differentiating with respect to R. We find the following. And this is what is called the mass continuity equation. It's just the kind of spherically symmetric, non-constant density version of mass equals density times volume. Okay? So it's a pretty straightforward equation. Okay, so we've talked about the forces that are in balance inside of stars. Now let's talk about energy transport inside of stars. So there are three main mechanisms for transporting energy within stars. There is radiation transport. This is, again, photons traveling out that are produced within the core and within the inner layers of the star, transporting energy out to the outer layers and eventually out of the entire star itself. So this is important when we have smaller temperature gradients. Well, smaller than what? Smaller than some particular value which is important for the second thing we'll write down. Okay. So another important mechanism is convection. So convection is what we mentioned when we looked at these convection cells on the star. Let me pause. We saw these kind of honeycomb-looking things where this hot material is rising towards the center, and then as it cools, it falls back down around these edges and forms these cell-looking patterns, just like you get in your coffee or teacup. Okay. And this transports energy. This is one way that the sun transports energy to outer layers or out of itself entirely by convection. And of course, convection is this physical transport of material traveling up through layers. So for this to happen, you need quite high temperature gradients to drive this process, and you can do some quantitative stuff with this and sort of estimate what particular temperatures you need for convection to dominate. But we're not going to do that. That's a sort of slightly more technical thermodynamics thing we won't go into. So this is important in stars with quite large temperature gradients. Important when there are larger temperature gradients. Why are they the size they are? Well, what will affect the size? I guess. I suppose the temperature gradient would affect the size, maybe. Maybe if you, I think if you. Yeah, I'm not sure what will affect the size. I mean, I definitely don't know how quantitatively you could calculate what size convection cells you would expect. This is probably something quite standard. I think someone that knows more about fluid dynamics than me would answer, but I can't think off the top of my head. I guess if you had a higher viscosity, viscosity tends to stop shearing processes, so stop fluid layers passing over each other. So if you had a high viscosity, I can imagine that you would have fewer convection cells. Well, would you have a smaller cell? I was kind of thinking you'd have a bigger cell for a higher viscosity. Yeah, right. That's just my hunch. Yeah, I'm not sure. That's my first guess, is that if you had a higher viscosity, you'd get bigger convection cells, just because you'd very roughly you would expect less kind of mixing between layers, less kind of shearing motion of the fluid, and I think you would minimize that by having larger cells rather than lots of small cells. But that's a very hand-wavy thing, so I guess the viscosity would affect it. I sort of have a hunch that the temperature gradient would affect it, but I can't think how it would affect it. Yeah, I'm not sure. This is probably something. This is probably like a classical fluid dynamics thing, not something you could answer with fluid dynamics in general, rather than thinking about in particular about stars. But I'm not totally sure. That's my only thought I have on it, really. That if you had a higher viscosity, you'd expect bigger convection cells. But I'm not even certain of that. Yeah, that's interesting. I'll think about that. Thank you. Okay, so yeah, convection is important. You need higher temperature gradients for convection to be a more dominant thing. Okay, but in our sun, within the core, radiation is dominant, and I think the further out you go, so you can certainly see this from when we looked at the picture of the outside of the sun, convection becomes more important. Okay, because I think you get steeper temperature gradients as you go out of the sun than when you're inside of the sun. Maybe we can show that using, when we derive these scaling relations, maybe we can try and show that you expect higher temperature gradients the further out in the sun you go. Or is that obvious? Is that obvious? Not sure it is obvious. And actually, the equation we're about to derive, this radiative transport equation, I'm not sure if it implies that either. But anyway, that's a diversion. We'll cross that bridge when we come to it. I'm not entirely sure. Okay. And there's a third energy transport mechanism, which is conduction. And this is only really important for compact objects, like neutron stars and white dwarfs. Conduction has, a very, very minimal, practically zero effect for ordinary stars, main sequence, red giant, or otherwise. Okay. And I think in white dwarfs, actually, the thing that does most of the conducting is actually the electrons, because I think the electrons are traveling considerably faster than the nuclei. Well, the protons, the nuclei that are also inside of the white dwarf, which I think is why they conduct heat better. I think the root mean speed does affect heat conduction, but I'd have to think about that actually as well. Okay, so we're going to introduce two new things. Well, two new quantities. We're going to introduce epsilon r, which is the energy generation or energy generated per unit mass per unit time. So it's the power the star produces at a particular radius at per unit mass that is at that radius. You thought it would. You thought what would? I forgot what we were talking about. As in, you thought the temperature gradient would... Oh, you thought it would have been because of density. Yeah, I guess, well, that would affect it too, I suppose. If you've got a heavier fluid, if you have a heavier fluid, you'd perhaps expect smaller convection cells, because they sort of will shrink down a lot quicker. So what did we say? We said for a higher density, you'd expect a smaller convection cell, and for a higher viscosity, you'd expect a larger convection cell. Yeah, I mean, they both sound reasonable to me. Yeah, maybe we'd... I'm sure there is some good source that you can look up, a fluid mechanics text or something that will talk about convection cells. I didn't think too much about convection cells in advance of this, but I think what we've said so far in the chat and what we just said about density sounds reasonable to me. I think it sounds reasonable. Yeah. Okay. What defines viscosity energy output? No, viscosity is I mean, you can define it as it's a property that's related to how momentum is transferred along speed gradients in the fluid. So if you have speed gradients between different layers of your fluid, this sort of transfers a momentum flux up through the fluid. And I think the velocity is a measure of how much that momentum is transferred. Or more qualitatively, it's just a measure of how sticky the fluid is. How well it can kind of flow over a boundary. What is the kind of stress, force that is what is the stress that is induced when this thing flows over a boundary is determined by its momentum. High viscosity means it has a high sort of dissipative effect in that it will dissipate momentum very, very quickly when it flows over a fixed boundary, or when you have flow differences in flow between the layers. It's kind of it's how sort of gummy it is. I mean, something like water is not particularly viscous. Something like custard is quite viscous. You can think of it in that way. It's how sort of gummy and thick it is in a way. All right. So that's the first thing we wanted to introduce, this epsilon r. Next, I want to introduce LR, L for luminosity. So this is the luminosity that is produced within this radius r, okay? Remember, we're always thinking about these shells of some radius r. And this is the luminosity produced within a radius r. Or in other words, because luminosity is just total power output across the entire area. Sorry, one second. We can also call this the total power produced within the radius r. Oh, I see. You meant how would the convection cells vary in viscosity? So what we were talking about earlier is I thought that you'd have bigger convection cells for higher viscosity. That's how it makes sense to me, but I'm not totally sure on that. My reasoning was viscosity tends to prevent mixing between layers. If something has a high viscosity, it's not good to have, or it will quickly dissipate gradients in the flow. By gradients in the flow, I mean a viscosity will dissipate two parts of the flow that are moving with different speeds. So if this part of the flow is moving very slowly and this part is moving quicker, a viscosity will dissipate that, so they kind of both end up moving at the same speed. So it tends to not like mixing between different layers of the flow. So I thought a high viscosity would mean we would expect fewer of these boundaries between convection cells, which would mean you would want to have fewer larger convection cells rather than lots of small ones. That's just my thought on it though. So I expect if you had a higher viscosity you would have larger convection cells, but I'm not sure. And then about what you said about density, I would expect if you had a higher density you would have more convection cells that were smaller. But I'm less sure about that actually. But anyway, yeah, that's what I think about convection cells. That's why I like these conversations, because I just sort of thought the convection cells, it's pretty fine, not particularly interesting. But then when you get questions about them, and you start thinking about it, these things are a lot more interesting than they first seem. So thank you very much for that discussion on convection cells. That was very interesting. I'll definitely look into that more afterwards. Okay. All right. So again, let's draw the familiar diagram we have of the star with some shell of radius r and a thickness dr. Okay. So we have all this material here. And what we want to think about is how much energy is passing through or being absorbed by this shell at the distance r. Okay, so the energy that is being absorbed by the shell or passing through the shell, either one, is what we've called Lr. So now we'd like to calculate that. And we're going to do this simply by conservation of energy. So whatever energy is generated within this radius here has to either be absorbed by or pass through the radius, this shell here, by this kind of, you can think of it as like an imaginary line through this shell, okay? And how do we calculate that total energy that is produced within the radius? Well, we've defined this quantity epsilon, that is the total energy produced per unit mass, okay? So we have to take the energy produced per second per unit mass and multiply this by the amount of mass we have within this entire inner part here. So again, we have the density and then the volume, or the summed over volume of all of these rings like this. And that gives us that total flux through or into this outer layer, okay? And now, just like we did with the mass continuity equation, we can invert this expression. We can differentiate both sides with respect to r, and we end up with dl dr is epsilon r rho r 4 pi r squared, okay? Come on, make a box. And I'm going to call this the energy continuity equation. dr bar. Oh no, well this shouldn't be a dr bar. Oh, I see. Oh yeah. Sorry, totally right. Got you. Okay, thank you. Yeah. No, thank you for pointing that out. So I'm going to call this the energy continuity equation. It probably has another name, but I can't remember it. Okay. All right. So remember, we talked about these three different forms of energy transport: convection, radiation, and conduction. Okay. And we're going to think now about radiation, because this is the most dominant form within the inner part of our sun. So we should be careful here, because we've said two things. So thermal pressure is the dominant form of pressure, that is the force supporting the sun, not radiation pressure. But in terms of pressure and force, radiation does not dominate inside of the sun. But in terms of energy transport, radiation does dominate. It's the radiation that dominates transport of energy from inner parts to outer layers. Okay? And let's try and calculate this. So the way we will think about this will be in terms of momentum flux. So we will think about how much total momentum flux is produced in this interior radius r, and then we'll think about how much of it is absorbed by this outer shell that is on the outside of this radius r. Okay? So kind of what we're doing here is we're thinking about the force that radiation is exerting on the star, but then we're going to change it from a force back into something involving temperature. Okay, so this is not the most dominant effect that is supporting the outer radius, the radius of this shell. This is not the dominant effect, the radiation pressure, but we're considering it as a kind of secondary effect, just for the purposes that it will help us derive this equation. Okay, so let's think about radiation pressure. So the radiation pressure from a black body source, and the sun behaves pretty much as a black body to a good degree of accuracy. The Sun is a fairly good black body. So from a spherical black body source, the radiation pressure is given by this. So let's explain some of these bits here. The 4/3 here, this is a sort of geometric factor that comes from the fact we're considering a spherically symmetric radiation field, or we're considering the normal component that is providing outward pressure of this radiation field. Because if you think about the star here, now every single part of the star is radiating isotropically as a black body. But we have to isolate the part of this radiation field that will give a normal pressure. So we have to kind of find the component of the pressure that is normal to the field here. And when you do that calculation, you end up with a sort of trig integral, an integral over a cos something. And you end up with this factor of 4/3 from doing that. Okay. So this is the pressure by a black body radiation source that is emitting isotropically. That is the pressure that is generated by it. Okay. So what we're going to do is we're going to equate the energy that is deposited into this outer layer at radius r, and we're going to equate it to the momentum flux that is absorbed by the layer. So the amount of momentum flux that the thing gains has got to be equal to the amount of momentum flux that is deposited into it. Okay, so this is again a conservation equation, except now we're thinking of conservation of momentum flux. And by momentum flux, remember, I just mean the momentum passing through a particular area. Okay, the flux of momentum. So the momentum flux absorbed by a given layer, well, we have the power, so the energy per second that is absorbed, that is passing through the layer. To turn that energy per second into a momentum per second, we divide by the speed of light, using E equals pc for photons. And then we have this factor here, that is the opacity. And this is just a measure of how transparent the material is. So you can imagine if this outer layer, radius r, we're thinking about, this shell, is totally transparent, then it doesn't matter how much energy is being pushed into it. None of it is going to be absorbed. Transparent things don't absorb energy. Well, don't absorb light like that. So if this symbol here, I can't remember what it's called. Is it chi? Yeah, I think it's chi. If chi was 0, then this thing would be totally transparent and it would absorb no energy. But in general, this thing will depend on a whole manner of things like the composition, how metallic the star is, its temperature. There are lots of temperature limits on this thing. So for different temperatures, the radiation will be absorbed or will be scattered in different ways. I can't actually remember how it works now. I think for high temperature, the opacity. I think for high temperature, the opacity just becomes constant. It doesn't depend on frequency. But anyway, we're just leaving it here as a constant factor. Okay. And then we also have the density and dr here, the width of this layer. Okay, because the sort of dr represents the thickness that the light is traveling through, the thickness of this layer. So if it has to travel through a very large thickness, you would expect that much more of it would be absorbed. So what we've got is we've got the momentum flux coming in, then the opacity, which is actually a measure of what proportion of the energy flux is absorbed per unit mass. So we therefore have the density here, and then we also have the thickness, because the thickness will affect how much of it is absorbed. So this is the momentum flux absorbed by the layer. And now let's consider the momentum flux that is deposited into the layer. And we will equate these things. Okay. So the momentum flux deposited into the layer, well, there's a minus sign here because the radiation pressure actually decreases the further out you go. So this minus is a sort of little fudge factor to account for the fact that we're thinking about the flux passing through. So even though dPdr is dropping, we want to think of this in a positive way, okay? And then we're multiplying by this little volume element of the layer, okay? So this is the pressure gradient times by the thickness, which gives the change in the pressure. And then we're multiplying by the area over which this pressure gradient is acting. Okay, so this is giving us the momentum flux that is being deposited into the layer. And we're equating these things. Equating these things is just a statement of conservation of momentum flux. Okay? So in equating these things, we have Lr over C chi rho r dr is equal to minus dp radiation dr 4 pi r squared dr. And of course we can cancel the drs, these thicknesses of the layer. And then we rearrange this as an expression for the luminosity as minus 4 pi c r squared over chi rho r times this gradient in the radiation pressure. Okay? But remember, we have an expression for the radiation pressure. For this isotropic black body, yeah, momentum flux is pressure, exactly, that's what we're doing. We're calculating the contribution of radiation pressure. We're just saying that the radiation pressure that is absorbed by a layer, which comes from this thing here, where, remember, chi is this kind of opacity factor that tells you of all the radiation pressure that is coming into you, how much is absorbed. And it's multiplied by this because it's defined in terms of per unit density, I think, or maybe it's per unit mass. I actually can't, I'll have to double check that. So this gives us how much momentum flux or how much pressure is exerted on the thing. I think it's better to think in terms of momentum flux because it's easier to think of momentum flux as being deposited. But momentum flux and pressure are the same thing, okay? And then this is how much this is how much momentum flux is absorbed, and this is how much momentum flux is being deposited. Okay, so we have this change in the pressure gradient. You have the change in the pressure gradient times by the distance multiplied by the area over which it's working. Okay, so this is kind of more like a pressure-y equation. So this one we think of in terms of momentum flux. This one I guess you can think of slightly easier in terms of pressure, because it's just a pressure gradient times by the distance over which you have the pressure gradient, okay? And we have this expression for the radiation pressure from a black body, which, to a good approximation, as we said, we can think of the sun as. The difference between absorbed and deposited, well, there's no difference in that we're setting them to equal. They're just different perspectives, if you like. So this is the perspective of how much the radiation pressure decreases by in going across the layer. So this is, if you like, the loss in momentum flux by the loss in momentum flux in crossing the layer, and this is the gain in momentum flux of the layer. And of course, these things have to be conserved. Just by conservation of momentum, these things are conserved. Okay. So we're taking our expression for the radiation pressure, 4/3 sigma t to the 4th over c, and now we're putting it into our expression here. So now now LR will be, it'll have this same prefactor, but now we're differentiating 4/3 sigma t to the 4th over c. Okay. And when you do that, from the chain rule, you'll see you'll get a t cubed out here, and we'll have a dt by dr in here instead. And if we rearrange all of that and keep track of all of the factors, we end up with an equation for the temperature gradient. So that equation is -3 the opacity times the density Lr all over 64 pi r squared sigma t cubed. So this is our radiative transport equation. This is the equation that governs radiative transport within the star. Okay. Alright, so this is another one of our equations of stellar structure that we wanted to come up with. So we've got these 4 equations so far, and we're going to use these to derive some scaling relations. So a reminder of what we have so far. We've got the equation of hydrostatic equilibrium. This equation which tells us that the outward pressure due to thermal or whatever else is balanced by, hello Cosmolano, Cosmolano, that tells us that the outward pressure that's due to thermal pressure, radiative pressure, degeneracy pressure, whatever it is, we don't care, is balanced by the inwards gravitational pressure. Okay. So we wrote this as d p by dr is minus g mr rho r over r squared. Okay, this is how we wrote it. Then we had the mass continuity equation, which said that dm by dr was 4 pi r squared rho r. This one is not particularly useful, but we only took a second deriving it anyway. Then we have the energy continuity equation that we derived second to last, which was this dl by dr is 4 pi r squared rho r, ooh, that's an ugly rho r epsilon r. And we had the radiative energy transport equation, which we just wrote down. It was this -3 chi rho r Lr over 64 pi r squared sigma t cubed. Okay, so these are the relations we have so far. These are called the equations of stellar structure, and you can get some others, but these are the ones we're looking at for now for a radiation-dominated energy transport and a the equation we have for hydrostatic equilibrium. It doesn't specify the pressure mechanism which is dominating the outward pressure, but when we come to look at our own sun, when we apply this to our own sun, we will of course be thinking about thermal pressure as dominating this equation for this red P here. Okay. So what else do we know? Well, we have another equation, an equation of state for our plasma, for our gas, and this is a bit of a sort of cheaty approximation one. We're going to use the ideal gas equation. And we're using this, one, because we're going for rough estimates, and two, because it's not actually that bad of an approximation. It gives you some pretty reasonable numbers when you use it. And as we're not worried about things like prefactors, in deriving these scaling relations, we're really only looking for rough kind of behavior. How, for example, the temperature of a star changes if you have a star of larger mass, etc. What would you expect otherwise besides pressure for other stars? Well, so we spoke a little earlier about the different possible kinds of pressure. So there's only really one kind of inward pressure, just to recap here, which is this gravitational pressure coming inwards. But then for outward pressure, there are sort of three sources. There's thermal pressure of the same kind you get if you have a balloon full of air. There's radiation pressure, because the photons, the electromagnetic radiation which is produced inside of the sun carries momentum according to E equals PC, and this can transport momentum and therefore deliver pressure into different layers of the star. And lastly, there is the most exotic of the three is this degeneracy pressure, which you only really have in compact stars like white dwarfs and neutron stars. So those are the three kinds of pressure we discussed. As far as I know, those are the only kinds of pressure you can have. Well, actually, I think quark stars, which I think probably don't exist but are one of these hypothetical things, I think actually the pressure that supposedly supports quark stars is not just simply degeneracy pressure. There's something else about that, because it's a strong interaction thing, but I really don't know much about that at all. So those are the kinds of pressure we discussed. So I'll remind you what the ideal gas equation is. I always remember it in this way, where n is just the number of molecules in the gas. But of course, it's not very useful to be thinking about the number of molecules in the star. Neutrinos too. Do you mean like what do you mean neutrinos? So there are neutrinos, as we'll see when we talk sort of qualitatively about this energy generation. We do get neutrinos produced. You certainly get a lot of solar neutrinos produced inside of stars, but they don't equate anything to pressure, because neutrinos are so weakly interacting. They pass through the sun with basically no. They have a very, very large mean free path. So large it practically. I don't even think the mean free path would be anything near the solar radius, I think. Cosmolo says, sorry if this is off topic, but do only outward pressures couple to the gravitational field, or does gravitational pressure exhibit some kind of self-coupling? Well, gravity does self-couple. That's very true. So as I mentioned a little earlier, we're only looking at Newtonian gravity in this case. If you're looking at very compact stars, so like when I mentioned degeneracy pressure, that is important for things like white dwarfs and neutron stars. If you're trying to work out these things for a neutron star, you would have to use general relativity, and I expect you could think about that, if you like, as being due to the self-coupling nature of gravity and how strong gravitational fields require general relativity, which is of course a highly non-linear theory. So you could think about that as self-coupling. But for the stars we're thinking about, where Newtonian gravity is perfectly okay and will give us reasonable things, because we don't have very compact objects. Stars are not particularly compact. They are significantly larger than their Schwarzschild radius. The Schwarzschild radius of the sun is, well, what would it be? It would be like 10 to the minus 11, 10 to the minus 30, 10 to the minus 19. Would be like a kilometer or something. In my head, I think. As far as I know, you could work it out. You could work out the Schwarzschild radius of the sun, which I think is around a kilometer. It's 2 gm over c squared. So this is like 10 to the 30. This is a 10 to the minus 11. So that's a 10 to the minus 10 to the 19 on top, and then you've got a 1 over 10 to the 16. So that's roughly 10 to the 3. So that's approximately a kilometer for the sun, and the radius of the sun is, I think, around 600,000 kilometers. We wrote it down at the start. What was it? The radius of the sun is 6 times 10 to the 8 meters. So yeah, about 7 times 10 to the 5 kilometers. So it's significantly larger than the Schwarzschild radius of the sun, which is why gravity is a good approximation. No, thank you for the question. It was good, because when I mentioned we're using Newtonian gravity, I never really clarified why that was a good approximation. And it's a good approximation because the Schwarzschild radius of the sun is about 1,000 times smaller than the radius of the sun. So that means if you're thinking about corrections to this, these corrections are going to scale in a very small way, these general relativistic corrections to what we're doing. But when you think about neutron stars, the radius of a neutron star is fairly close to its Schwarzschild radius. So then these things do become important. Maybe another time we'll do something where we talk about these compact objects and we kind of repeat what we're doing, but doing it with general relativity for these compact stars. Though that is quite a lot more complicated, actually. But I'm sure it's interesting. Okay, so thank you very much for that. Let me put that there for now. So we were just about to rewrite what the ideal gas equation looks like, because we don't want it in terms of volume and number of particles. We'd like it in terms of mass and radius if possible. So we're going to rewrite it as P equals density at, well, we don't need to, well, let's write it density at a particular radius, kb over T over the average mass of the particles that make up this thing, okay? And if you think about that, this makes sense. So what we're doing is we're dividing both sides by the volume, and that gives us the number density here, n over v. And an equivalent way of writing the number density, the number of nuclei that are inside of the sun, is the total number of, the total amount of mass per unit volume, and dividing that by the average mass of each molecule. And that will give us the average number per unit volume, which is this n over v that we would like when we divide by v, okay? So we'll use that more in a minute. When we come to actually calculate, we'll try and estimate the temperature at the core of the sun using this relation. But for now, we're just deriving very approximate scaling relations, okay? So in terms of a scaling relation, what the ideal gas equation tells us is that pressure is proportional to density and temperature. Now, of course, this is not a property of the star, this is a property of its composition, and this is just a constant, so we can forget about these things. So the ideal gas equation tells us pressure is proportional to mass times temperature over radius cubed. So where did the mass times mass over radius cubed comes from? That comes from the density here. The density of the sun, very approximately, is just its total mass over its total radius cubed, up to constants, which we're not caring about, just as a scaling relation, okay? What other scaling relations can we get? From the first equation, from our hydrostatic equilibrium equation, we can derive a scaling relation from this too. So dP by dr, proportionally, that is just P over R, the pressure on the inside of the sun over the radius of the sun. And then we have an M, another pressure here, and an R here, okay? So putting all this together, it's like we have P over R for the dP by dr term is proportional to mass, and then it's mass times density. So a mass over radius cubed, and the whole thing in the hydrostatic equilibrium equation is all over R squared. So that gives us pressure is proportional to m squared over R to the fourth. But we already have an equation for pressure. So we would like these two equations to be self-consistent. And if we impose them being self-consistent, you can see that we'll be able to rearrange an equation for T. So if they're self-consistent, then that means we have to have the top equation, mt over r cubed, is proportional to the bottom equation, m squared over r to the fourth. And if you rearrange that for T, that just tells you that T is proportional to m over r. Okay, so that's one important scaling relation. The temperature of the star is in main sequence anyway, is roughly proportional to its mass over its radius. So if you have very heavy small stars, these are going to be much hotter, whereas if you have very, very large stars, so you can kind of use this to think about what happens even when stars depart from the main sequence. So although these equations are derived from the equations that we've mostly thought about in terms of the main sequence, if you think about going into the red giant phase, well, the mass of the star stays the same when it goes from main sequence to red giant phase, but the radius increases substantially, and this increase in the radius will correspond to significant cooling, a decrease in temperature, as it enters the red giant. So as these things get much, much bigger, their total temperature drops. But interestingly, their luminosity increases substantially, because luminosity, remember, is this total power output over the entire surface of the star. There's a larger radius, and it sort of balances out, so the total power emitted by a red giant is larger than a main sequence, even though the temperature is quite a bit lower. Okay. So let's think about equation 4. This was this radiative energy transport equation here. So what kind of scaling relation does this tell us? Well, the left-hand side, we've just got a T over R for this derivative. The rho, remember, we will write as m over r cubed. Then we have the L, we have an r squared here, and we have a t cubed up here. Okay. So putting that all together, we have T over R is proportional to the density term, which is a mass over radius cubed, times the luminosity, times radius squared over T cubed. And now rearranging that for luminosity, that just tells us luminosity is proportional to R to the 4th over m times T to the 4th. But of course, we have an expression for T up here, a scaling relation, so we can put the T scaling relation into here. So that is R to the 4th over m times m over R to the 4th, which tells us that the luminosity is roughly proportional to the mass cubed. During the main sequence phase, this is anyway. Okay. And this is a useful scaling relation. We can use this to think about how long stars will spend in the main sequence phase. So if you think about the star, it supports itself by burning nuclear fuel. The amount of nuclear fuel it has is proportional to its mass. It's how many hydrogen atoms it has that are available to be fused together. And the luminosity is the rate at which it's burning these hydrogen atoms. It's the rate of energy production, how much total power is emitted by the star. So if you want to calculate how long at this particular rate of energy production a star with mass m will last, you can say that the time period for the main sequence is going to be roughly the mass of the star divided by the mass cube of the star. Okay, so that is m to the minus 2. So the amount of time stars will spend in their main sequence is proportional to 1 over the square of their mass, roughly. That is the scaling we've derived. But it turns out this is fairly accurate. This roughly agrees with, data from Hertz, from Russell diagrams and observation. So it's a pretty good equation we've derived for it. Okay. You wonder why it's the cube of the mass and not just the mass. Well, I mean, I guess we've just showed that through all of this, why the luminosity is proportional to the cube of the mass. Okay, it depends on a lot of these things. So we derived a lot of these equations of stellar structure, and then we've taken very simple scalings of them to show how they imply these scaling relations. Okay. So to summarize, this tells us that more massive stars die younger. Okay. Right, well, let's try and use this for something. let's try and estimate the core temp of the sun, core temperature of the sun. Okay. So what are we going to do? We're going to use the hydrostatic equilibrium equation. And we're going to use the mass continuity equation, which was equation 2. And these two things here are kind of dying to be multiplied together in some chain rule-y way to eliminate r. So that's the first thing we're going to do. I'm going to take this equation up here, equation 1, and divide it all by equation 2. Okay. So that gives me dp by dm is equal to minus gmr, because the rows will cancel, over 4 pi r to the 4th. Okay. Well, how can we use this? So, of course, the natural way you would think about using this equation would be to integrate both sides. Which is a perfectly good thing to do. You guess it's just find it weird conceptually because you're not sure of how to think of a cubed mass. You mean like dimensionally, as in like, are the dimensions wrong? Well, the dimensions are wrong because we have dropped all of these constants. So like, for example, to get this m cubed one, we used at one point, we used this equation here for the radiative energy transport. And, you know, we dropped a lot of things which do have dimensions that are important. So although they're constants, they do have dimension, you know, they have units. So unit-wise, L proportional to m cubed is not, it doesn't make sense dimensionally, but it's just a scaling thing. Okay, so there are loads of factors in here. This is why, you know, you could, if you like, you could try and put the constants back in with dimensional analysis. But I think it's probably not worth it because typically these scaling relations, they only really have power in as sort of seeing how a particular star, how long a particular star might live, for example, given you already know how long a star of a different mass, say, would live roughly. So, for example, the relation we have here for the main sequence lifetime, say you know the main sequence lifetime of the sun, which I think for people do have fairly good estimates of what that might be. It's what's supposed to be like. The sun is around 5 billion years old. It's got around another 5-6 billion or so left, I think. So if you knew that, you could then say, well, okay, there's a star up here that is about twice the size of the sun, twice the mass of the sun. How long will that live? And then, of course, you can use this scaling relation to say, well, if it's twice the mass of the sun, it's going to live 1/4 the length of the sun, because this is a 1/m² relation. Okay, but yeah, the units are we've dropped all these constants here which do have units, so that's a good point. Thank you. So that might be why it's a little unintuitive, because the units are different. Okay, so we've ended up with this integral by taking the mass continuity equation and the hydrostatic equilibrium equation, and then we've separated the equation and we're sort of getting ready to integrate it. But of course we can't just integrate this simply with respect to m, because r in itself will depend on m, or perhaps a better way to say it is that mr, the mass within a given radius, will of course depend on the radius you're going out to. And therefore if you think about writing an equation for mr in terms of r, and then inverting that to get an equation for r in terms of m, r will be a function of m also. So we can't just integrate this simply. Okay, but if we were, we would integrate up to the total mass of the sun from 0. And likewise on this side, the pressure corresponding to having no mass enclosed, or sorry, rather being at the radius 0, is this core pressure, and then the outside part here is this outer pressure in the very outside of the sun, which once you get, sort of outside of the atmosphere or into the stellar atmosphere is 0. Once you're out of the sun, there's no pressure around you because there's no sun around you, okay? But what we can do is we can place a bound on this integral. So as m increases towards the mass of the sun, r will increase towards the radius of the sun. Okay, that's how this function mr is defined. M at the radius of the sun is equal to the mass of the sun. So likewise, as the mass approaches the mass of the sun, the radius here will approach the radius of the sun for this function. And the radius of the sun is, of course, the largest radius we have in the problem. All of the other r's here will be smaller than the radius of the sun, which means we can place a bound on this integral and say that it is larger than, well, this minus the integral here, the same integral, but replacing the 1 over r to the 4th as rs to the 4th. I've just realised this has come invisible off the screen, so I will move it down. Okay, like that. So that is a bound we have on this integral. Okay. It has to be larger than this, because rs is the largest value that little r can take here. And of course, if we set it so that it's always at this large value, this integral on the left here will be smaller in size than the integral here. Okay. Oh, well, actually, because of the minus sign, actually, this is a little mucked up. Okay. Maybe what we should do is we'll cheat a little. We'll just take magnitudes of everything, because we know that eventually the minus sign on the left you get from the fact that the integration limit, the integration limits are kind of the wrong way around. So when you do these limits, you'll get a minus PC. So that will cancel this negative sign here. But what I'm going to do is I'm just going to cheat, and I'm going to put magnitude signs in so then it doesn't muck up the way I've written down this here. Okay, but don't worry about that. Okay. So that means we have a lower bound on the core. The core is greater than or equal to this integral here. Gm over 4 pi rs to the 4th dm, which we can evaluate, as now r is just a constant. We just have an integral over m up to the mass of the sun. So the core pressure is approximately greater than gm squared, g mass of the sun squared, over 8 pi radius of the sun to the 4th. Okay, that's a rough equation for the pressure. M is a function of r, that's right. It's a function of small r, but so remember what we did is, here we've got a differential equation that is in terms of m. Okay, so to solve this differential equation, we want to integrate with respect to m. So you're right, m is a function of r, and therefore, inverting that function, r is a function of m. Okay, but what we did here was in getting this bound, we said that if little r was just big R all the way through, that gives us a bound on this integral. But this integral here will always be bigger than this integral here, where little r now is taking the maximum possible value of r. Okay. But in doing this integral, we're only integrating with we have the variable is m, and we're integrating with respect to m. So we just get the half m squared. Okay. Yeah, that's right. The variable is m to integrate. Exactly. Okay. So this is our rough estimate for the core pressure, which we could calculate, but I think it's probably less interesting. I think it's more interesting to move straight on to the core temperature, because now we're going to try and calculate the core temperature using the ideal gas equation. Okay. and which again, remember, of course, the Sun is not really an ideal gas, but this gives us a reasonable order of magnitude. And when we get the number, we'll see that the number actually is not too far off of what much more sophisticated calculations give the mass of the Sun to be. So remember, this m bar here is the mean mass of particles in the Sun. So what particles are in the Sun? Well, to a good approximation, the Sun is mostly ionized hydrogen. Hydrogen, of course, is protons and electrons. So we have roughly 50% protons and 50% electrons. So if you wanted to work out the mean mass of a single particle, you would take the mass of the total mass of electrons plus the total mass of protons and divide it by the total number of all of those things. And because there are there's the same number of protons as there are electrons, there are 50% of each, your average mass will be roughly it will be one half the mass of the proton plus the mass of the electron. But the mass of an electron is about 1,000th the mass of a proton. So we're just going to approximate the mean mass as 1/2 the mass of a proton. Okay? All right. And we're also going to approximate the density of the Sun to be constant. So again, this is a bad approximation, but it'll give us a reasonable order of magnitude estimate. So the density of the Sun is roughly the mass of the Sun over 4/3 pi radius of the Sun cubed. Okay. So we have the core pressure. What we're looking for is the temperature at the core. So we're rearranging the equation of state here, the ideal gas equation, to give us temperature. So temperature will be given by m bar pressure over rho kb. And now we just have to sub these things in. Okay, that's what temperature is given by. So the core temperature is approximately greater than or equal to, is, order of magnitude around the core pressure we had, that was this gms squared over 8 pi rs to the 4th, now times these terms here. Okay, so that is 1/2 mass of the proton for the m bar, and then 4/3 pi rs cubed over mass of the Sun kb. Okay, so that gives us in total GMS 1/2 mass of the proton over 6 kb radius of the Sun. And if you plug all that in, which I won't do right now because it's quite long, it gives us the core temperature as a lower bound is roughly 2 million Kelvin. And I think the more sophisticated estimates are around 15 million Kelvin. So we've got this, within an order of magnitude, which for a very basic back of the envelope calculation is not too bad. Okay, it's not perfect. But that's a rough estimate for the core temperature. Well, now let's think about the actual mechanism that generates energy in the Sun. So the mechanism that generates energy is nuclear fusion. Specifically in our Sun and in most main sequence stars, this is fusion of hydrogen into helium, is this dominant process. Okay. So it is hydrogen to hydrogen, well, 2 lots of hydrogen plus hydrogen into helium is the dominant process. And this can take place through a few different mechanisms. The most prolific one is this pp1 chain, this proton-proton 1 chain, which I think accounts for around 85% of fusion in the Sun. And it takes a few different steps, and some of these steps take significantly longer than others. So the way this PP1 process works, so let's say we start off with ionized hydrogen gas. So we just have protons and electrons sort of moving around in a kind of soup. Well, the electrons don't do anything in terms of fusion. It's the protons that take part in this. So first we can combine two protons together. Okay. Two protons can smash into each other, and at a certain proximity, the strong force will take over. Of course, protons repel each other electromagnetically, but if they smash into each other enough, and well, actually we'll talk more about this because there is a subtlety to it. But anyway, somehow the protons get close enough to fuse together so that the strong force takes over and they form a single thing. So this is two protons will form, well, first, for a very brief period, they will form two protons, a diproton, something like that. But this is very unstable. So what happens is one of these protons will decay by the weak interaction into a neutron. And this process releases solar neutrinos and also positrons into the mix. But these positrons will annihilate pretty quickly with the electrons that are also present in the plasma. Okay. So this process here, this first process of combining the two protons is massively so the bottleneck in how quickly fusion happens. On average, for two protons, this takes about 10 to the power of 10 years. So this is by far the slowest thing inside of the star. Now, that doesn't mean that it takes 10 to the 10 years for a star to start fusing. It just means if you were to think about two, protons smashing into each other, or for any particular two protons, it would take roughly 10 to the 10 years for these things to happen in such a way that they will fuse. But of course, there are lots and lots of protons inside of the sun, so things do happen much more quicker than that. You do get fusion happening because, of course, we see that the sun is shining. Okay. Well, after this, or rather simultaneously to this is happening for multiple protons. Okay, so we now have two sets of these deuterium nuclei produced. Deuterium is a proton and a neutron together. Okay. And if we combine another proton with this deuterium nuclei, then what we get out, I should draw an arrow here to show this is a product. Then as a product of combining another hydrogen nuclei with this deuterium nucleus, we get a helium-3 isotope. Okay. Which is like this. But energetically, this still isn't done yet. So now there is fusion between these helium-3 nuclei. There's another proton there that formed this helium-3 nuclei. These helium-3 nuclei have to de-excite. They have to emit gamma radiation because the fusion process has left them quite unstable and energetic. So gamma rays are what nuclei emit when they're too energetic, when they're, sort of shaking about too much. They have too much kind of vibrational sort of energy. And now these helium-3 nuclei will combine. Ooh, they don't produce anything square. To produce a helium-4 nucleus. And two kind of fissioning protons, which are sort of shot off to maintain this nuclear stability. Okay. Oh, you actually made it to a stream. Nice. Good to see you, non-dairy neutrino. Okay, so this is this PP1 mechanism. It makes me laugh every time I say it because it's PP, but anyway. I should also have said this process here of this weak decay is very, very fast. This only takes about 1 second to go... sorry, not the weak decay process. The process where an extra proton is picked up into this nuclei takes only about 1 second. And then this process here of combining these two helium-3 nuclei takes around 1 million years. So this is again a pretty slow process. Not as slow as the 10 to the 10. That is by far the bottleneck in this process. Okay. So overall, this reaction looks like we start off with 4 hydrogen nuclei, and we end up with 1 helium nucleus, 2 positrons, 2 electron neutrinos, and 2 gamma rays as well that are sort of shot out. Okay. Do you ever wake up with a song stuck in your head? Yeah, all the time. Absolutely. What song have you got stuck in your head? Okay, so this is the net reaction. And the way this generates energy is that there's actually a deficit between the masses of what's on the left-hand side and what's on the right-hand side. So this helium nucleus here actually doesn't weigh the same as these 4 hydrogen nuclei that came before. It weighs slightly less. So overall, this reaction seems to have a sort of deficit mass to it. We end up with less mass than we started. And what happens to that energy? Well, it's released according to Einstein's famous equation. The Hanukkah song by Adam Sandler. Oh, I don't think I've ever heard that. I'm not a big Adam Sandler fan. Okay. So this is this energy released by this net nuclear process. And you can calculate exactly how much this energy is. You can calculate the change in mass is the mass of the 4 protons minus the mass of the helium nucleus. And you get around this number here, a very tiny amount of mass. But then this is multiplied by the speed of light, which is a very, very large, speed of light squared even, which is a very, very large number. So that gives us an energy released of about 4.3 times 10 to the minus 12 joules, or around 27 MeV. And of course now you could think about the rate at which these reactions happen. If you take the luminosity of the sun and you divide it by, the energy that is released by one of these reactions, you could find roughly the rate of these reactions. But actually it's nicer if you can calculate the rate using more theoretical considerations as a sort of quantum mechanics tunneling problem. But that's what we're getting to next. This is this practicalities of solar fusion. Okay. So I mentioned the way solar fusion works is that you have to have these nuclei, or these protons in this first step, have to be brought sort of close enough to each other so that they will overcome the strong electromagnetic repulsion that is keeping them apart. And if you think about this, the energy that's associated with that repulsion you can calculate. Let's say the protons have to be roughly sort of within the size of the nucleus. In order to fuse together, they have to be roughly within the distance of one nucleus away from each other, which is about a femtometer. So for them both to be within that, we say that they have to sort of be about 2 femtometers away from each other in order to fuse. So to push these 2 protons within a distance of 2 femtometers within each other requires delivering a potential energy of this much amount here, which is roughly 1.15 times 10 to the minus 13 joules, or 0.72 MeV. This is how much energy is needed to get these protons close enough to each other such that they can fuse. But recall, we calculated that the core temperature of the sun is roughly 2 times 10 to the 6 Kelvin. And now we could, if we liked, we could use the more sophisticated temperature at the core of the sun, which is the 15 million Kelvin roughly. But it doesn't actually make a difference. The factor of 10 is not important in showing what we want to show. So if you have this temperature at the core of the sun, that implies a kinetic energy per nucleus of 3/2 kBt. Okay, if you have a gas of, if you have an ideal gas of temperature T, then each molecule has kinetic energy 3/2 kBt. Okay, so again, ideal gas is a very much an approximation. Okay, and if you work that out, that gives a kinetic energy of about 4.14 times 10 to the minus 17 joules, or 0.00026 MeV. So compare these numbers. This is the energy these nuclei have, the kinetic energy they have inside of the core of the sun, and this is the energy they need to have in order to overcome this Coulomb barrier, to get close enough that they will fuse. But it's not enough, exactly. It's a factor of, it's about a factor of 1,000 too, well, more like 10,000 too small. So it's by far not enough. Well, how is this possible? How is it possible that the energy doesn't work like that? You wonder about the limit of stellar mass where the nuclear binding energy needs to include GR terms, assuming it's even reasonable consideration with quantum gravity. Okay, well, this is actually, we mentioned this a couple of times now. So in doing this, in thinking about normal stars, we're just using Newtonian gravity. And the reason it's okay for us to use Newtonian gravity is that the Schwarzschild radius of the sun, we sort of estimated earlier, is around about 1 kilometer. And the radius of the sun is around about 6 times 10 to the 5 kilometers. So it's considerably larger than its Schwarzschild radius. So GR effects are not important in this case. But if you were looking at something like a neutron star, or to a lesser extent, perhaps, I've not thought about it with a white dwarf, but certainly for a neutron star, then you would have to think about general relativity, and you would have to try and construct this setup using, like a Schwarzschild metric, where you would have an interior solution for the inside of the neutron star, and then you would have your external Schwarzschild solution, and you would, have to match the two up, and you would have to work with it like that. So yeah, a neutron star, you would have to consider GR, and maybe we'll do that another time. You were thinking a neutron star, but there's no nuclear stuff going on. Oh wait, what do you mean? You wonder about the... What do you mean nuclear binding energy including GR terms? I mean, nuclear binding energy, you can calculate it like from the semi-empirical mass formula or something, where the binding energy is related to, there's a term for the volume of the nucleus and the surface area of the nucleus. Then there are terms that talk about how the Fermi energy stacks of the protons and the neutrons together. I don't see why you would have GR would have an effect on that, on those particular terms. I mean, very high energy densities will affect GR, but I sort of don't see how GR would affect these relatively small, comparatively energy densities that you get from these nuclear reactions. I think it's more about how compact the masses are, is why you have to introduce these GR corrections in neutron stars. I might not follow what you're saying, but anyway, let's move on and talk about. Well, I'll move on anyway, and I'll talk about how this actually happens, because we've shown that the kinetic energy that these nuclei have is vastly smaller than the kinetic energy they need if they are to get close enough that the strong force can take over. So there are two mechanisms that assist with that. The first one is kind of something that we've just neglected throughout. So we've been talking about average temperature, really, and average kinetic energy. Okay, so when I wrote down the equation above where we calculated the kinetic energy of one of these nuclei, really what that is it's the average kinetic energy. Okay, but actually particles in a gas, and to a good approximation, these particles inside of the core of the sun obey a Boltzmann distribution. So their velocities are not all the same, they're not all equal to this average speed. They actually have some probability distribution of how many you can expect to measure with a particular velocity. So here, let FV be some, normalized probability that you would expect, how many molecules you would expect to find within a particular velocity range. Then this Maxwell-Boltzmann distribution looks kind of like this, okay? So it is sharply peaked at some max velocity. Well, sorry, not max velocity. Some the, I don't know, most. The one where the largest number of particles have that velocity. And then if you calculate the mean of this, the mean you can find is somewhere around here, the mean velocity. And this is what, yeah, exactly, most probable. And here is the mean velocity. This is what we've been calculating when we worked with kinetic energy is 3/2 kBt. This is like the mean kinetic energy is given by this. But it's not the kinetic energy of every single particle, because their velocities are distributed differently. Okay, so let's say we plot as well on here this v, this velocity that corresponds to a kinetic energy of 0.72 MeV. Remember, 0.72 MeV was this energy that's needed to overcome to get these things to fuse, to get these protons to fuse. Well, there is a non-zero number of molecules, of nuclei, sorry, that are traveling with velocity greater than that. So there's this tail here that says that some small fraction, very small fraction of the total number of particles will actually be traveling purely from this random nature, this random, this distribution of their particle velocities, which will affect them. Will it be relativistic? No. A kinetic energy of 0.72 MeV will be like around, what, like 10 to the 5 meters per second, I believe. Well, let's work it out. So if the kinetic energy is 10 to the minus 17, the mass of the proton is around 10 to the minus 27. That gives you around a velocity squared of around 10 to the 10, then a velocity of around 10 to the 5. So this is still 1,000 times slower than the speed of light. So relativistically, this is all fine. It's not until you get, pretty close to the speed of light, within sort of percents or tens of percents, that you get very significant effects. So no, this is not relativistic. We don't need to worry about that. But that's a very good question. Thank you. Okay, so this has one effect. This Boltzmann tail means that some of the particles will be traveling fast enough to get onto here. But there's another effect that is actually dominant compared to this. And this is a quantum tunneling effect. So we won't go into the details of this, but you can actually calculate the expected tunneling rate you have. And then from that tunneling rate, you can calculate things like the mean lifetime you'd expect of the sun. Because of course the tunneling rate will help you find out the rate of these nuclear reactions. And the rate of these nuclear reactions, if you divide it by the total number of these hydrogen atoms, divide it by the rate at which they're happening, that will roughly give you how long you'd expect the sun to keep on fusing as another crude estimate. But we're not going to do that, we're just going to talk about it sort of qualitatively. Okay. So nuclei can tunnel through the Coulomb barrier. Even though, as we've shown, the average kinetic energy is smaller than the kinetic energy needed to overcome this Coulomb barrier, nuclei will be able to tunnel through. So this Boltzmann tail we drew, this is saying that some nuclei do have speeds high enough to tunnel through. Sorry, not to tunnel through. The Boltzmann tail is nothing to do with tunneling. The Boltzmann tail is saying some particles do have high enough speed that they will be able to get close enough to fuse. But what the quantum mechanical tunneling is saying is that even if they don't have kinetic energy that is large enough to fuse, so even if they're not part of this Boltzmann tail, they will still be able to fuse, potentially, because quantum mechanically they can tunnel through this potential barrier. They don't have to get over the top of it, okay? In this standard way you think about tunneling quantum mechanically usually. So there is some probability for tunneling, which you can work out from, you think about a potential well and look at the Schrödinger equation, you can work this out. You find that the tunneling potential is always roughly like 1 over the kinetic energy square rooted, okay, is a rough probability for tunneling through a barrier. It does depend on the barrier height as well, but that's okay. And then if we want to plot, say, the Maxwell-Boltzmann distribution we just had, but now we want to plot it against kinetic energy. So the Maxwell-Boltzmann distribution plotted against kinetic energy is like an e to the minus KET. Sorry, e to the minus EK. Then the tunneling probability, the probability that any particle of a particular kinetic energy will tunnel, is given by e to the minus 1 over root EK. So if you take the product of these two functions, this is the probability you measure a particle to be within a particular velocity range, and this white one is the probability that particle within a particular velocity, well in fact it's kinetic energy, not velocity now, but kinetic energy is just velocity squared. So all I've done is I've basically, instead of putting velocity on the x-axis, I've got velocity squared on the x-axis. The product of these two will give you the probability that a nuclei with any kinetic energy will be able to tunnel to get through to the other side of the barrier and fuse. And if you take the product of these two functions, you get this kind of shape here, which is this total probability that the nuclei will fuse, given they have a particular kinetic energy. And actually this effect will dominate, okay? So if you wanted to find the total probability that any of these nuclei that have speeds between 0 kinetic energy and whatever max kinetic energy, you would just compute the area under this curve. That would give you the probability that all of your nuclei from 0 speed up to very, very large speed will tunnel. And likewise, if you want to find the probability that your nuclei will fuse by this Boltzmann tail, that is given by this area under here, okay? But this area under here is larger because this is essentially the same function we had for the Boltzmann tail, just written, yeah, the y-axis is probability. Sorry, I should have labelled that, thank you. Oh, where's my thing gone? Ah, there we go. Yep. This is essentially the same equation as above, just written in terms of v squared. Yeah, probability density, that's right. You'd have to integrate over kinetic energy to get the probability. This function up here is quite large. This is, this is an increasing function. So here we're increasing the value of this function up here. Actually, should this green function, should maybe come above here, shouldn't it? Yeah, I think possibly it should come above here, but it doesn't matter anyway. The point is that this total green area here is larger than this area here. So that means that this quantum mechanical tunneling dominates over this Boltzmann tail sort of effect. Okay, so without quantum mechanical tunneling, you couldn't have fusion inside of stars. This is the thing that really allows fusion to happen. So the sun wouldn't shine without quantum mechanics. So it is a very important effect. And I think that's really all I wanted to say about the sun and stellar structure. So we derived a few results. What did we do? We estimated the core temperature of the sun here, and we looked at this dominating mechanism for nuclear fusion, this pp1 chain within the sun. And leading up to all of that, in getting this core temperature and stuff, we derived these 4 equations of stellar structure. So about hydrostatic equilibrium, mass continuity, this one I called energy continuity, and then this radiative energy transport one. Okay, and we used all this to get a few of these results at the bottom, and the conclusion is that the sun couldn't shine, stars wouldn't work at all without quantum mechanics, which is rather interesting, I think. So I think that's all I want to say for today. I think we'll leave it there. We've gone for about 2 hours, which has left me suitably tired. Thanks for all the great questions in the chat. The one about convection cells, I'll think more about convection cells now because of that. So thank you very much. I'm thinking possibly I might keep on not doing. Am I at all? Oh, sorry. Are you at all familiar with the solar metallicity problem and/or helioseismology? No, I'm not familiar with either, I'm afraid. Yeah, no, sorry. Not at all. Not my area. I think if you were here at the start, you may have heard my disclaimer that I'm not an astrophysicist. Everything I know about astrophysics is stuff I can reasonably figure out from physics I do know. So I'm afraid I don't know any of that stuff. It does sound interesting though. Helioseismology sounds like, you know, if you were at a dinner party and someone told you they were a helioseismologist, that would be pretty impressive, I think. But no, I don't know anything about that, I'm afraid. What I was just about to say was I think probably I might keep on not doing, or as in like yesterday, so I didn't do my office hour yesterday. I think I might make that a permanent change to not do the office hour on Friday, because I think quite a few good people also stream at about that same time on Friday. And I suppose there's just not too much point, I think, than dividing it between several people that, you know, have similar viewers, you know, a lot of viewers in common. So I think I might leave that. But I'm thinking about something to replace it with on perhaps another day. Maybe something a little more structured than the office hour, like maybe just doing a sort of course or something, or working through a book together, perhaps on relativity, or trying to teach a sort of mini class on that. But let me know what you think. GR, yeah, possibly GR. Maybe it would start off with some SR and then gently ease into some GR. That would be interesting. Yeah, if you have any other suggestions, do let me know. Or if you want to let me know after this, you can, of course, join my Discord, which would be much appreciated, and then we could chat about it afterwards. And as I also mentioned at the start, if anyone wasn't here, the notes of what I've just done here, well, as in the notes I wrote in advance of doing this, you can find on my website. If you go to my website in my About section, go to the Twitch office hours part, and then at the bottom, it's something like stellar physics calculations, the notes I used for this session now. But yeah, so let me know. Feel free to give me any suggestions for what you might like me to cover if we did something more structured instead of the Friday office hour. I'll keep the Tuesday office hour and maybe make it a bit longer, as there'll only be the one. And of course, then there's Mario Kart on Thursday, and then this every Saturday. Next Saturday, I'm not sure what to talk about. So the idea is we could go through some other different planets, but then there's a lot of stuff that's more interesting than any of the planets. You know, it might be fun to talk about black holes at some point, or neutron stars, but I'll have a think. Feel free to let me know again in my Discord or in the chat what you might like. Comets. Yeah, comets could be interesting. It's just whether there's enough sort of meat to it to get some good calculations, because like I keep saying, I'm not an astrophysicist, so I don't remember a lot of stuff about these things, but I like to think about what I could figure out about them, or what we could work out about them together. And I'm not sure how much there is you could work out about comets without having to look up too much. Tides, yeah, that could be interesting. Tidal forces. That could sort of neatly come into... maybe we could just talk about moons in general, do a bumper thing about a few different moons. I'll have a think. Yeah, feel free to message, put it in the Discord if you have any more suggestions. But I think I'll leave it there for now. So thank you very much for joining, everyone that did. I'll upload the full video of this onto my YouTube channel tomorrow. So yeah, it was a lot of fun. Thanks a lot. Okay, bye everyone. Bye.